Good afternoon. Excellent. So the last time we talked about weak acids, and weak acids are different than strong acids. Strong acids totally dissociate into HVO plus the anion when you put them in water. And this has a very large K. Strong acids have a very large K, and they are completely dissociated, so the equilibrium is with the product, very much so. Weak acids don't dissociate completely, so that means there are reactants left on the left side, and with this, your K is smaller than 1. That's the difference between a weak acid and a strong acid. K is the first thing. And if you have a weak acid, it reacts with water just like a strong acid does. It reacts with water, and water is a base, to form the conjugate acid, and the acid becomes its conjugate base. So this is acetic acid, for example, becomes its conjugate base, and that's AC minus, the acetate ion. So the equilibrium constant for this is 1.8 times 10 to minus 5. It's smaller than 1, a lot smaller than 1. So this is a very weak acid, and with this, your pKa, that's the logarithm of that number here. That's minus 4.7, and you multiply with minus 1. That's our convention that we have to get from K to pK, and with this, the pKa is 4.7. Now, the next step is very different for weak acids compared to strong acids. So you have this acetate ion, that's a base here, and that base, of course it's not a very good base, reacts with the water to form undissociated acetic acid, HAC, plus OH minus. And for this we can now formulate a base constant, because this is a base here, and so that's the concentration of this times the concentration of this divided by the concentration of the free acetate ion. And this is 5.6 times 10 to minus 10. So it's a lousy base, okay? But it is a base. And with this, you can calculate a pKb. You take the logarithm, multiply it of this here, multiply it with minus 1. So you get pKb of 9.3. And then you have seen this is a conjugate acid-base pair here. So you see the acidity constant is given by this equation here, and the base constant is given by this equation here, which is the same than this here, okay? So if you multiply the acidity constant with the base constant of a conjugate acid-base pair, then you get what? So let's do that here. So these HAC is in the denominator here, and it's in the numerator here. That cancels. Then the AC is in the numerator here, and denominator here. That cancels. So we have then Ka times Kb is HVO plus times OH minus concentration, and we all know what this is. This is the equilibrium constant for water at that temperature, okay? So you can say this here is true. The same, of course, you can do the same thing then for a weak acid, a weak base, and its conjugate acid. The conjugate acid would be NH4 plus. There's the plus, it sits right here, it's a little bit shifted. NH4 plus reacts with water. Water is a base, so it takes this, forms H3O plus, its conjugate acid, and the acid becomes its conjugate base, NH3, okay? So what does that mean? So it produces here some extra H3O plus ion, gets more acidic, a little bit more acidic, and this one got a little bit more basic than compared to a strong acid or base, because it dissociates completely in its components, and that's it then, nothing happens. But here, with weak acids and weak bases, there's a second step involved, and we get to this today a little bit later. So when I left you the last time here, we had this question. We have two acids, HA1 and HA2, and we know that the pK of A1 is smaller than the pK of HA2. And so now you have that equilibrium, the acid 1 plus the ion of acid 2, the anion of acid 2 gives acid 2 plus the anion of acid 1. So that's obviously the stronger acid will win. And I'm asking you, is the K smaller than 1, equal to 1, or larger than 1 for this equilibrium here? Why don't? And you had plenty of time to think over this over the weekend, and you didn't think about nothing else. You only thought about this problem, okay? So I know that. That's why you're going to be able to answer this now with no problems whatsoever. So which one is true? Is the equilibrium on this side? Is the equilibrium on this side? Is K smaller than 1? Is K larger than 1? Or is it exactly 1? So this is what we had done at the beginning, or at the end of the last lecture. And many of you had voted. I think everyone has voted because you get credit for it. By the way, today, a year ago, it was over 90 degrees. I remember that when I gave that lecture. So there's two things you need to know. What pKa means, and if you compare two pKa's with each other, how does this precipitate is the wrong word. How does this work out for the Ka's? Okay, which one is the stronger acid? So it's the competition of the stronger acid, of the competition of the acids, and as in life, the stronger one always wins. Okay. So many of you said, or didn't say, that K equals 1. I agree with you, okay? But now you have to think about an answer. Is K smaller than 1 or larger than 1? So if HA would be a stronger acid than HA2, okay, then the equilibrium would go to the right here, okay? This would be winning then. HA1 would be winning. And with this, what would be, if the equilibrium would be here, so this would be larger and this would be smaller, so K would be larger than 1, okay? If HA would be the weaker one, HA1 would be the weaker one, so this one would go over here, then HA2 would be the stronger one. And with this, you have this divided by that, the products of those concentrations, and this would make K smaller than 1. So what is it? Think about your pKs and your Ks. I give you 1 minute for it. I got to get moving here. Where's Richard? Not here. Which is the stronger acid? 1 or 2? Okay, then you have the answer. But you didn't hear what he said. Okay, I go with C. Now, why is that? pKa1 is smaller than pKa2. What does this mean for the K? K1 is larger. Ka1 is larger than Ka2. And if this is larger, then it pushes the equilibrium to here. Okay? And with this is the answer. pKa1 is smaller than pKa2, and how to deal with pKs and Ks. So Ka1 is the stronger acid, and with this it pushes it to the right. That means there's more of this here in concentration and less of this, so this is larger than 1. Okay. Alrighty. Now let's do another one. We have, again, this darn acid 1 and acid 2, and we have pKa1 is smaller than pKa2, the same what we just had here. Now I have this equilibrium here. What is the K for this equilibrium? Is it A, Ka1 plus Ka2 is K, or K is Ka1 times Ka2, or C, K is Ka1 divided by Ka2? Why don't you think about this and give me your answer, please? Why don't you? Huh? What I would do, I would write both equilibria and then manipulate one of them, and then I would add it up to get that equation. Okay, there's no real distribution. The only one is it's a linear distribution. So the C's have the majority. So as I said to you, I would formulate both acid equilibria, and then I would switch one, and then we'll add it together, and with this you would see what the answer is. Why don't you do that? Discuss it with each other. So this reacts with water to form H3O plus A minus, okay? And this reacts with water to form H3O plus A2 minus. This one is K1 and the other one is K2. One thing you need to know, of course, if you have to add K's or multiply them to get the overall K. That's the question. Yes, we're getting there. It's still linear, but steeper now. Okay, I go with the, I think we take C, okay? I don't think so, I know actually. So what you do is you say Ka1 is that equilibrium. Ha1 plus water gives H3O plus A minus. Nothing wrong with that, isn't there? So you do the same thing for A2. Ha2 plus H2O gives H3O plus A2 minus. Okay, so that's Ka2. But we don't want this. The equation was written differently. We had A2 on this side here. If you look at this, it's the equation A2 was in this side. So we got to get A2 somehow over here. So why don't we multiply this with -1, and we switch the equation. We do this here. Now it's over here. A little bit too many arrows here. But this needs to, what do we do with this here when we switch that? It becomes the reciprocal, okay? 1 over Ka2, all right? So now, forget these arrows. If we subtract the arrows, we're not going to be okay, all right? So this is Ha1, okay, plus A2 minus, and this one here cancels against this one, and this one cancels against this one. So it's Ha1 plus A2 minus gives Ha2 plus A1 minus. So now we add it up. That's what I just did. So what is the K? Is K times K. Ka1 times 1 over Ka2 is Ka1 divided by Ka2. And with this was the right answer. Okay? So it's very simple, this stuff. All you need to do, turn it around and multiply it with -1, and then make sure that you look at the Ka appropriately. So, you know that salts, they have ions. And if you have a salt solution, for example, cooking salt, sodium chloride, if you throw this in water, it completely dissociates into sodium ions. These are positive ions, and chloride ions, these are negative ions, so cations and anions. And they can conduct electricity. They can carry electricity, these ions. So if you have water, for example, water, you have a lot of H3O plus and OH minus in water. How much do you have? 10 to the minus 14 is the product. So you have 10 to the minus 7 molar OH minus and 10 to the minus 7 molar H3O plus. That's not a whole lot, isn't it? So why don't I give you a couple of questions here? And I want to do the following. Let's see, I go down here for a second. If I could have the screen here, please. Not the screen, the demo. Thank you. All right, so you see we have solution 1 is HCl. That's this one here. Solution 2 is acetic acid. That's this one. As indicated there, it's both red. The solution 3 is water. Solution 4 is NH3 plus water, okay? And solution 5 is sodium hydroxide dissolved in water. So this has a pH of 1, 4, about 7, 10, and 13. So I have a lamp here. You see that lamp? This is interrupted. The circuit is interrupted. See these two prongs there? This is 110 volts is on there, okay? Don't do this at home, please. It's 110 volts, and I hope that Karen comes, that I don't electrocute myself. No, just kidding, okay? And so if I put this in water, you think that this would conduct electricity, that bulb goes on? What do you think? Dim, you think, dim, okay? I don't know, it must be on, okay? So now if I put this in solution number 1, that's the HCl. What do you think the bulb will be doing? Huh? Oh, there you go, lights up. Why? Because you have HCl is completely dissociated in H3O plus and Cl minus. And H3O plus is a high concentration, 0.1 molar, or we have, 0.1 was pH 1, 0.1 molar, and Cl minus conducts, is an electrolyte, conducts electricity very well. Now the next one would be acetic acid. Is this a bright bulb? So we have established this here already. This was bright, and now what this one? Would it be dim or dark? Why would that be? Okay, it's not so many of them there. Okay, there are some of them of AC minus and H3O plus, but compared to HCl, it's not completely dissociated. Actually, the equilibrium is very much on the left side. All right. So water we have seen already is, so this was dim here, and water doesn't conduct at all, or not very well, let's put it that way, okay? So what do you think what happens in sodium hydroxide? Will it be bright or dim? It will be bright. Anybody, any takers? Bright, okay. Oh yeah, it's bright, of course. The sodium is a strong base. It completely dissociates in Na plus and OH minus. So it carries the electricity very well. Now the ammonia is obviously a weak base. So what will be the brightness of the bulb? Dim. And that's correct, because the equilibrium is very much on the left side. The ammonia has not dissociated very well. There's only a little bit of NH4 plus and OH minus, and that's, you see, it carries the electricity, but not enough there to give you the full current, okay? So now we're going to do this here, and Karen will help me. So what we're going to do is, so this is what happened here, and this is what happened here. I leave you that here. So we mix now solutions 1 and 5. 1 is the HCl and the sodium hydroxide. And I ask you the first question, will it be acidic, neutral, or basic? That's the first question. Why don't you give me your answer, please? Acidic, neutral, or basic? So I mix HCl, pH 1, with sodium hydroxide, pH 13, and I want to know what happens to the pH. Pardon? Yeah, they are the same molarity. Yeah. Because 13 and 1 must be the same molarity. 0.1 each. Take your time, take your time. We are not doing it yet. If you have sodium hydroxide and HCl, and you pour them together, so what happens? Isn't it like a titration? Okay. Why is the what? No, this is the second part of the question. Okay. No. Just look at the pH at the first row. The second row is the next question. So will it be acidic, neutral, or basic? See, you got this. Of course, it will be neutral. So that means pH 7. You have the same amount of H3O plus here as you have the same amount of OH minus here, and they completely neutralize each other to pH 7 till they have water. You have water, so that's pH of 7. So now comes the kicker. Is when I do this and put the bulb in there, is it bright, dim, or dark? Why don't you answer that one? So we neutralized it, and I want to know if it's bright, is A, B dim, and C is dark.
Was answering the wrong question.
I did say it though. So we are now on the second part of the question. The bulb question. Does it conduct electricity very well, not so well, or not at all? So what is it? Let's see, what do you think? Okay. So you have sodium hydroxide and HCl. So the OH is neutralized by the HVO plus molecule by molecule. And since they are both the same concentration, so that's neutral. But what do we have left over? There was the sodium from the sodium hydroxide and the chloride from the HCl. You think it went up in the air, or where did it go? It's still in there, isn't it? So why don't you think about this? If it conducts electricity or doesn't conduct electricity, or it conducts electricity a little bit, and I give you 1 minute. You can discuss it with each other, please. Think about it. So what is it, Henry?
Because like
No. Yes.
why is it not C? I have all the hydrogen ion and hydroxyl ion combined to form one.
And what else is in the solution? I said it before. Okay, let's have a look at this. It shifted a little bit, huh? All righty, so why don't we do that then? Let's see, have a look at this. So if you could have the camera up there, please. Wait. We need to see everything. Wait. Not that they... So Karen will take solution 1 and 5, sodium hydroxide and HCl, and we will mix them. And they have an indicator in there which is sort of yellow when it's neutral. So you said the majority says that it will be conducting electricity, but quite a few people say that it is not conducting electricity at all, and some are a little bit, okay? So why don't we do that here? Oh my! Of course! What happened? You have sodium hydroxide and HCl. The hydroxide and the H plus or the HVO plus neutralize each other. We have established this. But you have left sodium plus, and you have chloride ions left. Sodium and chloride ion. They are strong electrolytes. Remember at the beginning I talked about cooking salt, sodium chloride, and that's a completely dissolved. It's a strong electrolyte. So with this, the light bulb is fully on. It conducts the electricity very well. So now this was the reaction, and with this we had neutral, and we had this. Now let's do something else. Switch that light off here, not to confuse you. Let's do solution 2 and 4. 2 and 4. So that's the solution 2 is the acetic acid. So that's a weak acid. And the NH3, the ammonia, that's a weak base. So we pour those together. First question, is it acidic, neutral, or basic? So you have a weak acid and a weak base, and you pour those together. What is it? A, acidic, B, neutral, C, basic. Pardon? Yes, you could actually. It's a little salty, but you could. Yeah. I was asked if you could drink the HCl when you neutralize it with sodium hydroxide. If it's properly neutralized, yes, you could drink it. It's a little salty, of course. That's not too healthy, but essentially, I don't recommend it. But essentially, you could drink it. If I would die of thirst, I would not drink it, okay? I would try to distill it. Okay, so you say neutral. That's good. You know why?
That's right.
Neutral is correct. So what happens? You have a weak acid, and this produces a little bit of HVO plus. And on the other side, you have a weak base that produces a little bit of OH minus, so they react with each other. That means Chatelier is at work. So you take away product here and take away product there. So then the acid makes more HVO plus, and the base makes more OH minus, and they neutralize again. And this goes on until all the acid is dissociated and neutralized, and all the base is dissociated and neutralized. Okay? So, but what do you have in solution after that? So you have water, obviously, because you have a neutral pH. You have pH 7. But what's left in solution? So what does the light bulb do? So you have in solution left what? Okay, why don't you tell me what the light bulb does? What ions do we have in there at the end? What's the conjugate acid of NH3? And what's the conjugate base of HCl? Oh, of acetate, I'm sorry. What's the conjugate base of acetic acid? Has nothing to do with it anymore. Okay, discuss this. Come on, you can discuss it right in the first. You actually do it anyway. In the first try. What means yes? You are sure about that? I'm not so sure about that. Why don't you discuss this with each other and give me another answer? Is that the third time I give you 30 seconds? Okay, you have what you have? NH4 plus and AC minus, okay? You have a neutral solution. So what happens to the electricity? Okay, last, come on, click in. Click in. Okay, why don't we do that experiment? So you neutralize, we have established this. You neutralize to neutral. You shift the equilibrium constantly by taking away the OH, and on the other side by taking away the HVO plus. So you're making more of HVO plus and more of OH till it's all gone, till all the base and the acid is in solution, okay? Now you have left over NH4 plus and AC minus. Are these ions? Okay, are there strong and weak ions? I don't know about any strong and weak ions, okay? They have a minus charge and a plus charge, okay? So what do they do if we do this? Okay, let's have the camera on this, please. So we're adding the the ammonia to the acetic acid. Go ahead. What does it do? Yeah. Wow! Of course, acetate minus NH4 plus, that carries electricity, and very strongly. It doesn't matter that this came from a weak acid. It's an anion and a cation, and it has a plus charge and a minus charge, and with this it carries the electricity. And with this, I think the A's have it. And so there it is. This is what's left over at the end. Okay? And that was neutral and bright light. So let's have a look at this. We can also solve it this way. The acetic acid reacts with water. So this is the acid. It's the base. That becomes the conjugate base here of this here. That's the base, that's the conjugate acid, and that's the conjugate base here. Okay, so that's the one, and the ammonia is the base, and that takes a proton from here. So this is the acid then, that's the conjugate base, and that's the conjugate acid. Okay, alrighty, so we can do that here. And so we have also the water equilibrium. HVO plus OH minus is 2H2O. Now we add this up. So we have acetate plus ammonia, this water, these two waters, and this here cancel, okay? This HVO plus and this HVO cancel. With this you have NH4 plus AC minus. And if you look at the K of this here, this is Ka1 times Kb1 divided by Kw. We know that this 1.8 times 10 to minus 5. And since it's by accident, essentially, they have the same base and acid constant number. So you can square this. This is 1.8 times 10 to the minus 5. This is 1.8 times 10 to the minus 5. We know that the water constant is 10 to the minus 14 at this temperature. And with this, you have a K of 3.2 times 10 to the 4, a huge equilibrium on the right side. So it is fully on this side here, and it conducts electricity. So now we're going to talk a little bit more. Let's switch that off here, and let me take the plug out that nobody electrocutes himself or herself. So we'll be talking now about titration of weak acids and weak bases. Did you do titrations in the lab? Okay, that's a little far. All the solutions are there, huh? We're not going to get there anyhow. All right. So you did titrations with a weak acid. What acid did you use? That was a strong acid. Any weak acids you did? Any weak acids? You did weak acid.
Use acetic acid.
Acetic acid, okay. That's our example. Let's say our example here. So you have your pH, and you titrated it with a standardized solution of sodium hydroxide that has OH minus. And so at the beginning, you have your acid, and you titrate it with base. It makes H2O plus A minus. That's the end, actually, of that reaction. At the beginning, you just have HA in water, which makes H3O plus and H2O. H3O plus A minus. This reacts with water to make H3O plus the acetate ion, okay? So now that H3O plus, you take this away. As I explained earlier, you take this away with this OH that you add. Le Chatelier principle at work. So you're making more of H3O plus because you took away the product, and now you're making more product. And this happens as long as this is still here, and then when it's gone, then you cannot make any more OH, and you have passed the neutral point. So this is how one of these curves looks like. And so you have this region here, and you have this region, that's the equivalence point. So this is the amount that you come to a neutral pH here. And we call this region, I just call it A. This region is called the buffer region. You see there, the buffer region, nothing happens here. So as I explained to you, whenever you add some OH, so you take away some H3O plus from this equilibrium here, and nothing happens essentially. You keep adding OH, and the pH is not changing very much. And this is what actually a buffer is. You have an acid with its conjugate base. If you mix this, then you get a buffer region which responds not very well at all to changes in pH. Or the pH doesn't change if you add acid or base. Okay, we will talk about this also in detail. And then you have the region here where you have this one reacting with water. The A minus will react with water. And then you have the boring region here, D, where nothing happens anymore because you keep adding OH minus, and so this will go asymptotically like this, all right? So you just keep adding. Everything that happened has happened already. So here we have the initial concentration of HA. So if I have acetic acid, 0.1 molar, and I have HCl, 0.1 molar, which pH do you think will be higher or lower? Will be the acetic acid higher, or the HCl have a higher pH? Or do they have the same pH? The acetic acid will have a higher pH because HCl is completely dissociated. All the H3O pluses are made, and the acetic acid has only much less H3O plus because the equilibrium is very far on the left side. The K is smaller than 1, much smaller than 1. So with this, the pH will be higher. That means you have less H3O plus in the solution. Okay, that's the first thing. So, or you could make a solution of pH 1. You would take 0.1 molar of HCl, but you have to take a lot more of acetic acid in order to get to pH 1. Okay? You could make solutions of pH 1, but 0.1 molar HCl, but much, much more acetic acid to get to pH 1 than compared with HCl. So this is our buffer region. This is this here, and reacts with this here. This is the buffer. And then we have here this where the acetate, the conjugate base of the acid here, reacts then with water. There's something going on. And here we have just plain OH. So you can do the same thing, of course, for bases. It's the reverse. You go here, and will be the pH of a 0.1 molar sodium hydroxide be lower or higher than the pH of a 0.1 molar ammonia solution? Which one will be higher, sodium hydroxide in pH or ammonia if you have the same concentration. Sodium hydroxide, exactly, because you make less OH for the weak base, all right? So that will be a lower pH, will have less OH minus ion. So, okay, there are these regions here. So let's look at region 1. So we haven't done anything. When we throw the acid, or we carefully put it in water, we put it in water, and then we calculate that initial pH. That means you have the acetate reacts with the H2O to make H3O plus AC minus, and you can expect, as we already speculated, a pH larger than 1 and smaller than 7. So if this is 0.1 molar, okay, so this will be then X, and this will be X, because it's same concentrations, same number of moles here, 1 actually. So this we can call X, and this we call X. And this will be dissociated away from this here. So we call this the concentration in equilibrium, 0.1 minus X. All right? So I can now say the concentration of this times the concentration of this. This is X times X is X squared, divided by the concentration of the acetic acid. That's my equilibrium, is 0.1 minus X, is Ka. And I know this is 1.76 times 10 to the minus 5. That constant. Okay, now I can solve that here with a quadratic equation, and many of you obviously know how to do that, but since that here is so small compared to 0.1, I say, okay, 0.1 minus x is about 0.1, okay, it changes in the fourth decimal, it's 0.1, and as I simplify this, I assume 0.1 minus x is about 0.1, and with this x squared here is 0.1 times Ka, and I take the square root out of this here. X is then 1.33 times 10 to the minus 3. And what is that? What concentration is that? That's the H3O plus concentration. So I take the logarithm of it, multiply this value with minus 1, and I get a pH of 2.88. All right? So, as you already said so rightfully, the pH is higher if you have a 0.1 molar weak acid solution compared to a 0.1 molar strong acid solution. What's the pH of a 0.1 molar strong acid solution? pH of 0.1 molar strong acid solution. Come on. Log of 0.1 is what? Minus 1 times minus 1 is 1. pH is 1. Okay, you got to have this down pat. I don't want to lie under your knife when you're a surgeon if you don't know what a pH is. Okay? That's very, very important. And I don't want to hear from these guys who have their lecture before you come in here that you don't know what a pH is. All right? That's important that you know what a pH is. All right. So now let's think about this. We have a solution, and we just say HCl. And this has a pH of 3. What's the concentration of H3O plus if you have a pH of 3? pH of 3 is what? 10 to the 3. Minus 3. Okay? So what is it? 10 to the minus 3 molar. Okay? That is pH 3. What would be pH 4? 10 to the minus 4 moles per liter. Okay? So you have a pH of 3 and you dilute it by a factor of 10. So you have the same amount of H3O plus ions, but you diluted it now by a factor of 10. What is your new pH? Why don't you think about this and give me your answer quickly? So the number of H3O plus ions are the same, but you have a larger volume. Remember, it's moles per liter. So what is the pH? You throwing at me? No. That's really important for all of you. Okay, if you are in public health or in nutritional science or in molecular biology or in medicine or wherever, even physicists will have to know what a pH is. Okay, everybody in? Come on. So this is not clear. We will discuss this then on Wednesday. I see you then. Good luck.